So for determining the independence of a set of functions, we don't have row operations per se to deal with, except sort of we do. So we have an interesting tool in the toolkit. It's called the Wronskian Determinant. So most of the time we'll just call it the Wronskian, so I'll put determinant in parentheses. So the Wronskian determinant of some functions f1, f2, etc. So these need to be a bunch of functions that are all defined on a common interval. And they need to be sufficiently differentiable so that we can take their derivatives. Then the Wronskian is denoted with w of the f's, and it's actually in general going to be a function. So we'll say w of x, and most of the time it's too bulky to write all this junk, so we'll just call it w of x. The way that you define it is you make a determinant, and across the top you put the f's, so you have f1, f2, out 2, fk, and then you just start differentiating them. So then you have f1 prime, f2 prime, out 2, fk prime, and f1 double prime, f2 double prime, out to fk double prime. And how many times do you differentiate them? Well, we want to take a determinant, and you can only take the determinant of a square matrix. So you make a square matrix. And so that actually means that the last one here is going to be the k minus 1th derivative, but it's not really important to remember that because it has to be square matrix. So now the interesting thing about this crackpot construction is that if w of x is non-zero for any point, so for any x on some interval I, then that set of functions is linearly independent on that interval I. Okay, so this will be the tool that we use. So let's look at an example. So back at the beginning, I told you that 1x and x squared form an independent set. Now, if I was being careful, I would have specified an interval and said, these three functions are linearly independent on, and then given you an interval. Like we could do this one for the entire real line, or maybe for the interval between 0 and 1, or whatever. Anyways, let's use the Wronskian now to check. So if I look at the Wronskian of 1x, x squared, then this is going to be, so I put 1x, x squared across the top of my determinant, and then I differentiate 1, and I differentiate x, and I differentiate x squared, and then I do more derivatives. So differentiating 0 gives me 0, differentiating 1 gives me 0, differentiating 2x gives me 2. This happens to be an upper triangular matrix, so I immediately see that the determinant is just the product of the diagonal entries. And so 2, and so this function 2, this is it looks like a number. That's secretly a function. That's the constant function 2. So it has a graph that looks like this, right? And this function happens to be it has non-zero terms on any interval in the real line, because it's in fact non-zero everywhere. So this means that 1x and x squared is independent on any interval I. All right, let's look at another example. Suppose we consider e to the x, e to the minus x, and cosh, the hyperbolic cosine. Well, you know in advance that this should tell us that this is a dependent set because cosh looks like half of e to the x plus half of e to the negative x. So let's see what happens and see if that in fact bears out. So the Wronskian of e to the x, e to the minus x, cosh x. So we'll have e to the x, e to the minus x, and cosh x across the top. And then we differentiate, so differentiating e to the x gives us e to the x and then e to the x again. If we differentiate e to the minus x, we get negative e to the minus x and then back to e to the minus x. And if we differentiate cosh, we get sinh, and if we differentiate sinh, we get cosh. There's no minus signs popping up like there are with regular cosine and sine. So we've got to take this determinant, and at first it looks like a god-awful nasty mess. And then you realize that this third row is exactly the same as the first row. And so with one row operation, we can see that the determinant is going to be 0. And so this Wronskian is 0 everywhere. So it's in particular it's 0 on every interval. And so the conclusion you can draw from that is that this collection of functions is linearly dependent on any interval.